Hello and welcome back. Okay, in the last video on the SNES controller, I built the circuitry necessary to read the data out of the controller and just display it in some LEDs. And that involved generating a latch signal and shifting the data out with the clock signal and storing the data via the shift registers in the output latches. So I'm expecting that to be the first of 3 videos, and this is the second one, where I'm hoping to interface the SNES circuit we built back into the main CPU circuit and read the data out from a bit of program code. In the third video, I'll design a PCB up and interface it in a final circuit. Okay, let's take a look. So here's the circuit we built last time. We got the clock input, which we're expecting the crystal to be on another circuit board, but we divide that down by 16 using a counter just to make the overall frequency a little bit more reasonable. We have a counter to generate the latch signal every 16 ticks. We've got an inverter we use for a number of things, and then we've got the shift and latch registers. If I power it up, I can push any of the buttons and generate an output LED. We've got 12 possible outputs, and the top 4 bits we've only ever seen as 0. This is apparently an ID for the controller, but for the physical controller, those are always all 0. The first controller circuit I built was for reading from a NES controller, and that had 8 inputs. And the CPU has a bus, and allocated to the controller I've got a single control line to instruct the control circuit to assert to the bus, i.e. we're reading from it. And that was going to be fairly straightforward. We'd plug those inputs into a 541 line driver, connect the output of those to the main bus, and then we'd have the control line hooked up to the active low enable. When we told the controller device to assert to the bus, it would just push those 8 inputs out. And that would have been very simple, but we've actually got a different problem now. We've extended the circuit to include 4 more lines from the SNES controller's additional buttons, and so we're not going to be able to go with that plan anymore. The obvious solution is to divide them up into 2 groups. We put a line driver on each of them, and then we build some kind of a circuit that's going to multiplex the 2 different line drivers onto the single bus. Now, in an ideal world, we'd have 2 different assert lines that would allow us to do this, or we could use a flip-flop to alternate between them and have some kind of external mechanic to synchronize the flip-flop so we know which state it's in. Now, when I roughed out the original plan for this whole system, I included the 1 read port for controller. And so what I'd like to do is try and come up with a way of including this extra functionality without bringing any other system resources to bear. So what we need is a system that allows us to work out what the state of that flip-flop is at any given point in time. And once we know the state of the flip-flop, we can keep track of it. We read 2 sequential bytes and we've got all the data we want. Now I do want the low half to be the full 8 bits of the NES controller, but what I'm thinking is I output the other 4 bits to the low 4 bits over here, but then the top bit I pull high permanently. So then when I'm first initializing my controller code, I can just read and see which byte has the top bit set. Now clever viewers will immediately think, well, what if the right button is being held down on the control pad? But if I write my controller reader code such that if it ever sees that top bit not set, then we know that must be the low byte, and I can just discard an extra byte from the I/O port and recalibrate myself to the correct way round. And if someone's going to switch the CPU on and permanently hold the right button down, we probably don't have to worry about behaving perfectly in that circumstance. So let's have a go at building this. Okay, this bus control circuit that we built in a previous video is going to be handy for testing this. And I'm going to use this line here to stand in for the load line that's going to be on the register. Okay, so what I want to use is a pair of line drivers for outputting 2 chunks of data. So these are the 74LS541s. We need power and ground. So we've got 8 output lines at the top on each, so we're going to tie those together and connect them to a stand-in bus. So now we have the 8 inputs, and then we have an output enable on each side of the chip. I'm going to connect 2 of these output enables together. So then the other output enable lines I'm going to tie high, and for now I'm going to make the lower ones low. These are active low enable lines. Actually, go yellow for these. Okay, so the first 8 lines we want to bring out to the inputs on this right hand line driver. And the next 4 I'll bring across to the second one. I'm going to take the next 3 bits from the next 3 bits in the shift register. We're not expecting those ever to be 0, but I don't think it's going to be particularly difficult to bring those bundles of wire across alongside the others. And then just the most significant bit we're going to pull high, and that's going to be our identifier so we know which is which. So let's plug the bus in. Okay, so if I take the active low for this one low, then that line driver is driving the lower 8 bits onto the bus. That's cool. We turn that to high, and now I take the active low for this line driver, put that low, and now that top bit is permanently on, and that's the signal we're going to use to determine which of the 2 registers we've pulled in. Now all of these buttons don't have an effect, but the new ones do. So now we need the circuit to actually select one of these based on a read signal. So first thing is we're going to use the read signal as an active low on the output latches. So now it's only possible for those to put the output onto the main bus when the read signal is low. Okay, that's good, that's working in exactly the way I'd hoped. And now what we need is a flip-flop that is going to change state each time we select it. Now the chip I'm going to use is a 74LS193, and I can almost sense some people rolling their eyes because I use these an awful lot. I've used 2 of them previously in this particular circuit, and that's actually why I favour this chip. I've got a big tendency to avoid putting a different device into a circuit and increasing the complexity of the BOM. Power and ground. The count down I'm going to bring high. The count up I'm going to take from our load line. Reset is active high, so we want to bring that low. And the load line is active low, so let's bring that high. Now, let's take a look at the least significant bit with one of our convenient LEDs over here. So now, each time I push the button, it flips. Now, using this to enable the active low enable lines on the chips, you've probably seen me build the circuit before with a 138 demultiplexer. And that would give me the option to both do the selection and enable the outputs singularly with the active low load line. But the line drivers we're using here have the 2 separate enable lines, so we can avoid that. We just need this enable line to be the inverse of this one. So we'll take the output to one of our spare inverters, use the output of that. Let's temporarily visualize those. Right, so we push a couple of buttons here, and that's outputting the high 7 bits plus our indicator, but then we load again, and it outputs the lower bits, which contain our 2 button status flags. Now I load, and we can see that left shoulder button, its bit is enabled. Load again, and I see the Y buttons bit is enabled. Now there's only a couple of small things we need to do to this circuit to finish it off. Now firstly, I'm outputting there, so this is the high byte, but as I change these buttons, it's going to change the output state. So if I push a button while this is asserting to the bus, we're going to be changing the value we're pushing onto a bus, which is not good. It's kind of breaking the contract we've got with the CPU. Now, when I make a point about this, I do get a few comments that say, with the specific circuit that's reading the data in at the moment in the CPU, that's not going to make a difference because I'm just pulling it into a latch chip. But we do want to actually honor the standard we've set for bus operations. Now, in other circuits, instead of a line driver, I've used a D-type latch as the output, and I've signaled the latch to load when the load line goes low, and then I just kind of keep it so it samples the data. But we don't have that here. In fact, if we swap these out for latches, we wouldn't have the second enable line, and then we'd need the demultiplexer, and we've added an extra chip. But what I'd like to do is change this circuit so it no longer responds while I'm pushing a button, and it has that same behavior of sampling the data right up until the point where I pull that load line low. And the way I'm going to do that is up here on this clock divider. Now, we've got 4 data inputs we really should be setting to something. We're just using kind of simplified breadboard circuitry to leave them floating. On the PCB, we'd have to pull all of the unused inputs either down or up. So I'm going to pull all of these inputs down so that then if we initiate a load, we get zeros. Now, instead of pulling the load line on the counter up, we'll have a line that we take from our load input. Right, so if you think about what's happening here, now that was loading the top half, let's load the bottom half. Even if I let go here, these outputs are not changing because the clock signal here is no longer being generated, and more importantly, the latch isn't being generated. And as soon as I release, it returns to normal operation and the status of the LEDs change. That is absolutely brilliant. I really like this circuit. When I first started to think about it, I could only see a 4-chip solution to adding this functionality. But by making it 3 chips, it's actually saved me a whole breadboard because I was previously thinking I'd have to stick an extra one on top or something. So I really like this circuit. It does everything we need. We've got a clear-cut way of identifying which byte is which, so we can read all 12 bits in. That's cool. Now we need to hook a device line up here, so we're going to want power and ground. But I think now it's time to get the main build out, plug this in and see if we can make it work. Okay, so here's the main build. Now here we've got the audio circuit, and I think I'm going to move this out just to make room for those breadboards. There's also a specific reason for that. The I/O port that we use for the audio circuit, we only use the write port for it, and that read port is unused. So we're actually going to stick the controller onto the same port as the audio. Only one's write only and one's read only. Alright, so we want to connect the main bus up. And then the I/O port lines. And this should provide power to the board. Okay, so now we're going to need an instruction for reading the controller input. And we're going to need a spare instruction. Now we've kind of used all of our opcode space, so we're going to have to find one to remove. But when we built the first VGA circuit, we did reserve an instruction for outputting to VGA, which we're not using. Let's use a shorter name. There it is. So we're replacing this output VGA instruction. We've declared a new line that we're going to assert, and then we load into A. Looks like we put the load and assert lines for audio in, and we only want the load one, and we've got the assert for the controller. Excellent. Looks like we've got an instruction for audio. So actually, I'm going to use that one. Makes more sense. And then 030 is a unused instruction. Okay, so pipe 2A has changed. Right, let's power it up, although it's not going to do anything. So this is working in the build okay. Just means that's getting power, I suppose. Let's write some code that can read this in. Right, I've created a stub controller read function. We're going to return the 12 bits of controller status, or more specifically the 8 bits we read in A and B. Right, so we read in from the controller data port. If we do that twice, we know we've got the correct 16 bits. Now I want to arrange it so this is the correct order. So the first one we read in is actually the top 8 bits. Right, so the top bit goes into the sign bit in the flags register, so we can actually use the sign conditional to act on that. So if the top bit is 0, we know we've got it wrong. So if the sign bit is set, we move on. If it's not set, we definitely know we've read the wrong byte in, so I'm going to read a byte in. Now obviously we could make this determination incorrectly if someone is holding the wrong button down at the point where we make this read, because that will look like the top bit is set, but we only need one read to happen with that button not held down and it will kind of self-heal the state. And then we have an init function which just makes that determination and fixes up the state if it wasn't what we expected, and that should be enough actually to make it all work. Right, let's write some test code. Okay, so we call control init, read the controller state, convert it to a hex number, write it to the console, add a new line, and then loop back. Right, let's give that a test. Okay, so that's streaming out 8000, which is just that top bit set. That's the first button. Ah, awesome. That's working perfectly. Ah, this is absolutely brilliant. That controller interface is working. Something I want to check is what happens if I unplug the controller. Right, that kind of works. I think the shift register we've got here has an internal pull-up, and because we invert the data return from here, it's going to work okay, but I don't like that. With the connector unplugged, we effectively have a floating input to this inverter. So let's just stick a pull-up resistor on that, and then that makes us a little bit safer. And that shouldn't interfere with the operation of this circuit. Outputting a hex number like this, that's kind of boring. Let's see if we can hook it up to something. Okay, I've got a great idea. Let's see if we can make Snek use the controller. Let's get some defines in here to make the coding a bit easier. That's the low B button. Y. Then we need to store the ones for the high byte separately. It's going to be the A button. Okay, so I have quickly hammered support for the controller into Snek. So the main bit here is I added controller support for up, down, left, right. But I also created custom wait any key functions for the menu operations, which also respond to the controller instead of just the UART keyboard input. Let's give that a quick go. All right, this looks promising. Now I wired this to the start button. Excellent. Unfortunately, it appears that the controller support hasn't made me any better at the game. But it works. Okay, I really enjoyed that. It's a nice little circuit and it worked really quite smoothly and integrated nicely. It does occur to me that this is the first time we've got both input in the form of the controller and output in the form of VGA without needing any secondary devices attached like the serial terminal through the UART. Now, when we first had that, I wrote the Snek game to demonstrate that functionality, but I think now would be a good time to develop something more visually interesting without needing anything else attached at the same time. So that's going to be the thing that I'm going to spend a chunk of time on over the coming days. I think a lot of people are going to find what I've got planned quite interesting. I'd like to extend extra special thanks to my first patrons. I've only had that open for a few days, but the level of support I've received has already blown me away. Thank you very much, everyone. There's a link to that and to the Discord in the description. As it is, I hope everyone found this interesting, and I hope to see you again very soon. Okay, goodbye.